Hi, Stu Schwartz from MasterMathMentor.com. This is video BC11. The topic is polar coordinates, area, and arc length. It covers the BC manual pages 56 through 59. This is the Indianapolis Motor Speedway, home of the Indy 500. The racetrack is a perfect oval. Given its dimensions, a grade school student would be able to determine its length and the area enclosed by it. This is the Watkins Glen International Raceway in Watkins Glen, New York. Trying to find the length of the racetrack and the area which it encompasses is a much greater challenge. Suppose we had another race called the Polar International that was held on this racetrack. This track is based upon a polar curve. How would we even go about trying to find the length of the racetrack as well as the area that it encompasses? By the end of this lesson, we shall be able to do so. Back in our geometry days, we learned how to take the area of a circle. We found it to be A is equal to pi r squared. That is equal to 1/2 of 2 pi r squared. We can now generalize this formula for a sector of the circle where theta represents the central angle when r is the radius. And we say that the area of the sector is equal to 1/2 theta r squared, where theta is measured in radians. So suppose r is 3 inches and theta is equal to 30 degrees. Our area is 1/2 of 30 degrees times pi over 180 degrees times 3 squared. We are multiplying by pi over 180 to convert the 30 degrees to radians. And we get A is equal to 1/2 pi over 6 times 9, which is equal to 3 pi over 4, and that is 2.356 measured in square inches. Now suppose instead of a circle, we used any general curve, which we will call R, which is f of theta. And we would like to find the area of the sector from alpha to beta. How would we do that? We will do the same as we did when we found area under a curve using Riemann sums. We will first take our theta and divide it into n little thetas. We'll call them theta 1, theta 2, theta 3, ... theta n. We know that alpha is less than theta 1, less than theta 2, less than theta 3, less than theta n, which is less than beta. So for these little sectors, we will call r sub I equal f of theta sub I, representing the radius of those sectors. And we will also call delta theta I equal beta minus alpha divided by n. Since all the little sectors have the same angle, we're simply dividing by how many there are. So to get the area of any of our little sectors, we say that a sub I is equal to 1/2 delta theta times f of theta sub I squared. Therefore, like with Riemann sums, we say that the area of n sectors will approximately equal to the summation, where I runs from 1 to n, of 1/2 delta theta times f of theta sub I squared. To get the actual total area, we use an infinite number of sectors. So A is equal to the limit as n approaches infinity of summation I equals 1 to n of 1/2 delta theta times f of theta sub I squared. So we come up now with our rule for area of a sector. If R is f of theta and is continuous and non-negative on the interval theta 1, theta 2, then the area of the region bounded by the graph of R is equal to f of theta and the radial lines theta equals theta 1 and theta equals theta 2 is given by the formula A equals 1/2 the integral from theta 1 to theta 2 of f of theta squared d theta, or the simpler formula 1/2 integral from theta 1 to theta 2 of r squared d theta. The graph of r equals 4 sine 3 theta is a 3-leafed rose as shown to the right. We would like to find the total area enclosed by the curve. Using symmetry, it is easier for us to find the area of one petal of our rose and then multiply it by 3. The petal in the first quadrant is traced as theta runs from 0 to pi over 3. So our area is 1/2 the integral from 0 to pi over 3 of r squared, which is 16 sine squared of 3 theta d theta. We can slightly reduce our work by using symmetry again, realizing that half of the petal is traced out as a theta runs from 0 to pi over 6. So the area in the first quadrant will be 2 times 1/2 integral from 0 to pi over 6 of 16 sine squared of 3 theta d theta. And the 2 and 1/2 cancel, and we're left with the integral from 0 to pi over 6 of 16 sine squared of 3 theta d theta. If you are allowed to use the calculator, by all means, put the expression in and calculate the answer. However, we can actually integrate this by using the power reducing formula sine squared theta is equal to 1 minus cosine of 2 theta all over 2. So our area becomes 16 times 1/2, or 8, integral of from 0 to 6 of 1 minus cosine of 6 theta d theta. And when we integrate that, we get 8 theta evaluated from 0 to pi over 6 minus 4/3 sine of 6 theta evaluated from 0 to pi over 6. That gives 8 times pi over 6 minus 4/3 times the quantity sine of pi minus sine of 0. And that gives 8 times pi over 6, or 4/3 pi, minus 0. So our first quadrant area is 4 pi over 3, and therefore the total enclosed area is 4 pi. The entire curve is traced out as theta runs from 0 to pi. You can integrate this from 0 to pi and you will get the right answer. But when the curve crosses itself and the r becomes negative, it is dicey to do that. It is always suggested that you take a simple area where r is positive, calculate it, and use the symmetry features to calculate the total area. If you are doing this by calculator, you put your function in R1. To do the calculation, you go to Math 9, which is FNINT, of R1 squared, comma, theta, comma, 0, comma, pi divided by 3. R1 is found in the vars, yvars 3 polar menu. A harder type of problem is to find the area of a section of a polar curve. This is illustrated in number 2. Find the difference in area between the outer and inner loops of the limacon. R is equal to 2 sine theta minus 1. This problem would be difficult to do without a graphing calculator, both for graphing the function and for taking the integral. The graph R equals 2 sine theta minus 1 graphs a limacon because it looks like a lima bean. We see it is comprised of an inner loop and an outer loop. We are looking for the difference in area between the loops. So we're interested in the difference between the blue area and the white area. Usually, to tackle a problem like this, we need to find the values of theta where the inner loop starts and stops, and where the outer loop starts and stops. We do this by setting the polar curve equal to 0, where r equals 0. We get r is equal to 2 sine theta minus 1 is equal to 0, sine theta is equal to 1/2, and theta is equal to pi over 6 and 5 pi over 6. In order to set up our integral, it is important to understand how this graph is generated. When theta is equal to 0, r equals -1. So we are at the rectangular point, -1, 0. We follow the arrow and we get to the origin. That occurs at theta is equal to pi over 6. We travel through the inner loop, and when theta is equal to pi over 2, we are at the top of the inner loop. We then continue down back to the origin, and that occurs at 5 pi over 6. We now travel counterclockwise along the outer loop, going completely around and ending back at the point -1, 0, when theta is equal to 2 pi. We start by calculating the total area. That is 1/2 the integral from 0 to 2 pi of quantity 2 sine theta minus 1, quantity squared, d theta. That is 9.425, and that represents the blue area plus the white area. We now calculate the inner loop area. That area is 1/2 the integral from pi over 6 to 5 pi over 6 of 2 sine theta minus 1 quantity squared d theta. We can use the fact that this is symmetric to the y-axis and write it as 2 times 1/2 the integral from pi over 6 to pi over 2 of 2 sine theta minus 1 quantity squared d theta. The 2 and 1/2 cancel, and we are left with 0.544. So the outer loop area is simply the total area, 9.425, minus the inner loop area, 0.544, to get 8.881. Finally, the difference in areas is the area of the blue, which is 8.881, minus the area of the white, which is 0.544, to get 8.337. In number 3, we're asked to find the area inside r equals 3 plus 2 sine theta and outside r equals 2. We know that r equals 2 graphs a circle, but unless we have a calculator, we're unsure what r equals 3 plus 2 sine theta is. So we will graph them on the interval 0 to 2 pi. R equals 3 plus 2 sine theta is the dimpled curve in blue, and r equals 2 is the circle in red. We are interested in the area that is shaded in blue. That is inside the curve r equals 3 plus 2 sine theta and outside the circle. We start by finding the values of theta where the two curves meet. So we set them equal to each other. 3 plus 2 sine theta equals 2 gives us sine theta equals -1/2, and theta is equal to 7 pi over 6 and 11 pi over 6. We can represent 11 pi over 6 as negative pi over 6. This is important for integration purposes. The area that is enclosed must be defined by an integral as we increase from the smaller angle to the larger angle. If we use 7 pi over 6 to 11 pi over 6 in our limits of integration, we enclose the bottommost region between the red and blue. That encloses the section outside the blue curve and inside the circle, and we don't want that. So the correct answer is A is equal to 1/2 the definite integral between negative pi over 6 and 7 pi over 6 of quantity 3 plus 2 sine theta squared minus 2 squared d theta. And our answer is 24.187. In number 4, we have the same setup, but we're asked to find something different. We are asked now to find the area of the region common to r is equal to 3 plus 2 sine theta, and r is equal to 2. We shade the region of interest, which is inside the circle and also inside the blue curve. Since this problem is the same as on the previous slide, the points of intersection are the same. Our game plan to find the common area will be to find the area of the total circle and then subtract the lower section area between the limacon and the circle from 7 pi over 6 to 11 pi over 6. The area of the circle is easy, pi r squared or 4 pi. The area of the lower section will be 1/2 the integral from 7 pi over 6 to 11 pi over 6 of the difference between each radius squared. So it is 2 squared or 4 minus quantity 3 plus 2 sine theta squared d theta. Again, we can make life a little bit easier by saying that is 2 times 1/2 and take the integral from 7 pi over 6 to 3 pi over 2. When we calculate that, we get 2.196. So our area of the red region is 4 pi minus 2.196, or 10.370. In number 5, we're asked to find the points of intersection for the polar curves r is equal to 2 minus 4 cosine theta and r is equal to 2. We first graph the two polar equations, and we find that r equals 2 minus 4 cosine theta is a limacon, and r equals 2 is a circle. It appears that there are 3 points of intersection. To find them, we set the two equations equal to each other. 2 minus 4 cosine theta equals 2, giving 4 cosine theta equals 0. And that gives cosine theta equals 0, and we have theta is equal to pi over 2 and 3 pi over 2. So our polar points of intersection are 2, pi over 2, and 2, 3 pi over 2. But we said that there were 3 points of intersection. What happened to the point of intersection at the point -2, 0? Here's the explanation. When theta equals 0, for our limacon, r is equal to 2 minus 4 cosine 0, which is -2. So our polar point for our limacon is -2, 0. But when theta is equal to 0, r is equal to 2. So our polar point for our circle is 2, 0. So what we're finding is that theta equals 0, the curves are at different locations. So they do not intersect, even though they pass through the same physical point. When theta is equal to 0, the limacon is at the point -2, 0. When theta is equal to pi, the circle is at the point -2, 0. They pass through the same point, but not at the same value of theta. The problem of finding intersections of two polar graphs is the same as finding collision points of race cars going around a track or satellites circling the Earth. The cars or satellites may occupy the same point in space, but do not collide as long as they reach those points of intersection at different times, meaning values of theta. A collision only occurs if the car or satellite reaches the same point in space at exactly the same time. For problems 6 and 7, you are to find the polar points of intersection and then confirm graphically. 6 reads r is equal to 5 quantity 1 minus sine theta and r is equal to 5 quantity 1 plus sine theta. Setting them equal to each other, we end up with 10 sine theta equals 0, and that gives us sine theta equals 0, meaning that theta is at 0 and pi. So our polar points are 0, 5, and pi 5. The graph confirms the 2 points of intersection. The third point, the origin, is reached by the red curve when theta is equal to pi over 2, and by the blue curve when theta is equal to 3 pi over 2. On number 7, we have r is equal to 2 minus 3 sine theta, and r is equal to sine theta. To find the points of intersection, we set them equal to each other, and we get 2 minus 3 sine theta equals sine theta, or 4 sine theta equals 2. Sine theta is equal to 1/2, and therefore theta is equal to pi over 6 and 5 pi over 6. So our polar points are 1/2 pi over 6 and 1/2 5 pi over 6. We see our graphic confirmation. Our 2 points of intersection are 1/2 unit from the origin at angles of 30 degrees to the x-axis. When theta is equal to 0 degrees, the circle is at the origin while the limacon is at the point 2, 0. The pirate has a map of the path he must take to get to the buried treasure. Unfortunately, it is in polar form. Let's help him find out how far he has to travel. We start with our arc length formula for curves in parametric form. It's stated that L is equal to the definite integral from t1 to t2 of the square root of dx dt squared plus dy dt squared dt. We can convert that to the integral from alpha to beta of the square root of dx d theta squared plus dy d theta squared d theta. We can write x and y in terms of theta. We know that x is equal to r cosine theta and y is equal to r sine theta. So dx d theta is, by the product rule, cosine theta dr d theta minus r sine theta. And dy d theta is sine theta dr d theta plus r cosine theta. So we can write dx d theta squared plus dy d theta squared as cosine theta dr d theta minus r sine theta squared plus sine theta dr d theta plus r cosine theta squared. Expanding these expressions and then factoring, we get dx d theta squared plus dy d theta squared is equal to dr d theta squared times the quantity cosine squared theta plus sine squared theta plus r squared times the quantity cosine squared theta plus sine squared theta. And that simply becomes r squared plus dr d theta squared. So our arc length is simply the integral from alpha to beta of the square root of r squared plus dr d theta squared d theta. So, formally stated, if r equals f of theta, whose derivative is continuous on the closed interval alpha to beta, then the arc length of the polar graph from alpha to beta is given by the definite integral from alpha to beta of the square root of f of theta squared plus f prime of theta squared d theta, or simply the integral from alpha to beta of the square root of r squared plus dr d theta squared d theta. In problems 8 and 9, you are given two curves and are asked to find the difference in arc length between them. In 8, we are given two spirals, r equals theta in blue and r equals e raised to the theta over pi in red, when we're looking at these over the intervals 0 to pi. The graph is shown and the length of the spirals appears quite similar. The length of the blue spiral is given by the definite integral from 0 to 2 pi of the square root of r squared, giving us theta squared, plus dr d theta squared, which is simply 1, d theta. And by the calculator, this is 21.256. The length of the red spiral is given by the integral from 0 to 2 pi of the square root of r squared, giving us e to the 2 theta over pi, plus dr d theta squared, which is e to the 2 theta over pi divided by pi squared d theta. And that turns out to be 21.064. So the difference is very small, 0.192, with the blue spiral being slightly longer. In number 9, you're asked to find the difference in arc length between r equals 2 plus 2 cosine theta and the circle with radius 5. We are not given an equation for the circle with radius 5, and we can put it anywhere. I chose to put it close to the cardioid to show that the circumference of these are relatively close. The arc length of the cardioid is the integral from 0 to 2 pi of the square root of r squared, which is quantity 2 plus 2 cosine theta, quantity squared, plus dr d theta, which is negative 2 sine theta, quantity squared, which is 4 sine squared theta. When we expand that, we end up with a 4 sine squared theta plus a 4 cosine squared theta, which gives us a 4, and the cardioid's length will be the integral from 0 to 2 pi of 8 plus 8 cosine theta d theta. This turns out to be exactly 16. The circle, we know, has a circumference of 2 pi r, which is 2 pi times 2.5, which is 5 pi, which is 15.708. So the difference in their lengths is 0.292. Although not included on the AP exam, we introduced the concept of surface area of a solid formed by rotating the polar graph r equals f of theta on the interval alpha through beta. We can rotate it first around the polar axis, which is theta equals 0, and get the formula S is equal to 2 pi integral from alpha to beta of f of theta sine theta times the square root of f of theta squared plus f prime of theta squared d theta, or simply 2 pi integral from alpha to beta of r sine theta square root of r squared plus dr d theta squared d theta. We can also rotate it about the polar line theta equals pi over 2, which is like the y-axis. S is equal to 2 pi integral from alpha to beta of f of theta cosine theta the integral of f of theta, square root of f of theta squared plus f prime of theta squared d theta, or 2 pi the integral from alpha to beta of r cosine theta times the square root of r squared plus dr d theta squared d theta. Number 10 asks to find the surface area by rotating r equals cosine theta about theta equals pi over 2. R equals cosine theta is a circle, and when we rotate it around the line theta equals pi over 2, we get the shape shown on the screen, which is called a torus. It's like a donut or a bagel with no real hole in the center. The circle is traced once as theta goes from 0 to pi. So since we are rotating about the line theta equals pi over 2, s equals 2 pi integral from 0 to pi of f of theta cosine theta, which is cosine theta, times the square root of f of theta, which is cosine theta squared, plus f prime of theta, which is negative sine theta squared. And that ends up to be pi integral from 0 to pi of 2 cosine squared theta d theta, as cosine squared theta plus sine squared theta is equal to 1. Using the identity that cosine of 2 theta is equal to 2 cosine squared theta minus 1, we can rewrite this as s is equal to pi integral from 0 to pi of 1 plus cosine of 2 theta d theta. Integrating that, we get pi times theta plus sine of 2 theta over 2, evaluated from 0 to pi, getting pi times the quantity pi plus sine of 2 pi over 2, and we get exactly pi squared. So let's finish where we began. We have the Polar International Race, whose track is based upon the polar equation r equals 1 minus cosine theta sine 3 theta on the interval 0 to 2 pi. We would like to calculate the area that the track encloses as well as its length. Assuming that r is measured in miles, the area is easy. It is 1/2 the integral from 0 to 2 pi of quantity 1 minus cosine theta sine 3 theta, quantity squared, d theta. We do this on the calculator and we get 3.927 square miles. The arc length follows its formula as well. It is the integral from 0 to 2 pi of the square root of the function, which is 1 minus cosine theta sine 3 theta, quantity squared, plus the derivative of the function, which is negative 3 cosine 3 theta, plus sine 3 theta, quantity squared, d theta. We end up getting 11.326 miles. To do this on the calculator, we let r1 equal 1 minus cosine theta sine 3 theta, and rather than us take the derivative, let the calculator do the work and say that r2 is n deriv of r1 comma theta comma theta. So on the home screen, we take the integral, fnint, of the square root of r1 squared plus r2 squared, comma theta, comma 0, comma 2 pi. The r1 and r2 are found in the vars, y-vars polar menu. When we calculate this, expect it to take several minutes. There are several points of non-differentiability or close to non-differentiability, and it takes the calculator quite a while to get through this. Generally, it's going to take about 2 minutes before an answer will pop up.